nouns. Okay? The stuff in chemical reaction. Okay. So those are the chemicals we're going to react. So today we're going to expand our language to include verbs and adjectives and adverbs. Okay? Because today, now that we can talk about chemicals, we can talk about chemical reactions. So we're going to jump from about halfway through chapter 9 and do part of chapter 11. We'll come back to chapter 10 in the middle. So today we're going to learn how scientists talk about chemical reactions. And the overarching theme is chemists are lazy. The reason why they why their name rules are about being lazy. How little can I write and give you all the information? Okay? So now we're going to take big, long, complicated things and turn them into something much shorter. And so chemical reaction. When things react, chemists think about it as two separate parts. And those two separate parts are divided in time, before and after. The stuff you start with is called the reactants. The stuff you poured in is the reactants. The stuff that reacts is the reactants. And products are the substances you end up with. Okay? Products are the stuff you end up with. So you've got reactants and products, before and after. Pretty easy to decide? I like the fact they name them the things that react are the reactants, the things that are produced are the products. So what happens is the reactants turn into products. But that is way too much for a chemist to write. So instead of turn into, they write an arrow. So the arrow is the verb. Turn into. It separates before and after. The arrow always has to point to the right. You can't flip the arrow around. If you think it goes the other way, you got to flip the whole equation around. Because chemists are used to looking at arrows that point to the right. And so when they look at a reaction, they're just going to see automatically just read right arrows. They look at the stuff at the right to see what they're supposed to make. So the arrow always points right. So Dalton told us what happened in a chemical reaction. Dalton, to explain what was happening in a chemical reaction, he needed atoms to explain what was happening. What happened to the atoms in a chemical reaction? Did you make new ones? Did you destroy the ones you had? You just took the ones you had and rearranged them, right? Dalton said that a chemical reaction is a rearrangement of the atoms. No new atoms are created or destroyed. So today we're going to use the formulas we've been working for the past few days to describe reactions, shortening them up. Okay? So we're going to describe reactions, and we're talking to see how we can make it shorter. And actually, in making it shorter, we get more information. We actually get information by making it shorter, which is strange. Usually, when you narrow things down, you get less information. We're going to get more. Okay, so here's a description of a chemical reaction. Copper reacts with chlorine to form copper 2 chloride. So this is saying I started off with an orange metal and a yellow-green gas. At the end I was done, I had some green crystals grow on top of my orange copper. The reactants, the things that reacted were the copper and the chlorine. The product, stuff that was produced was the copper 2 chloride. That's a lot of writing. Let's shorten it a little bit with a word equation. Here's the same thing, a little bit shorter. Copper and copper plus chlorine arrow copper 2 chloride. So that's the same thing? Exact same information? What is that plus sign? What does that stand for? Plus sign. Combined with and, so reacts with. So that means that there's two of them, they react together, right? So it's talking about there's this and that. And so the plus sign is our conjunction, right? Conjunction, junction, how does that function? Open up words, phrase. It's our conjunction. So we've got verbs now, the arrow. We've got conjunctions, right? Now, copper plus chlorine makes copper 2 chloride. That is still too much to write. So we're going to have some other symbols along the way. They're in your book on table 11.1, and most of them are common sense. There's a few special ones. The arrow, we've already talked about. That's what separates reactants from products. It's our verb. It means reacts to form, turns into, becomes, makes. It's the verb. Arrow is a lot faster to write than reacts to form. Okay, so reacts to form. It's my verb. The plus sign means and. It's not conjunction. Sometimes chemists need to be a little bit more specific about what their chemical looks like. So now we're going to add some adjectives that modify our nouns, our chemicals. They're pretty simple adjectives. If you write an S after the formula, in parentheses, you write the formula out and then you put parentheses, little s. It's not sulfur, it's a lowercase s. And that means that that stuff is a solid. If I put a G in parentheses after the formula, that means the stuff is a gas. Pretty obvious? You know what the next line is going to say? L means liquid. Yeah, fluid. Technically, the fluid. A liquid is a kind of fluid because air is also a fluid. Okay, fluid means they can flow. Okay, so both air and liquids flow. So gases and liquids are both fluids. We don't think of it that way, but they both move. Okay, now that sounds like all the possibilities. Now, there might be the fourth kind of matter is plasma. You're not going to have a chemical reaction with plasma because plasma means it's been heated and all its electrons have been knocked off. Is it going to be able to react if all you got is positive ions and electrons floating around separately with each other? No. So plasmas aren't going to react. But there is one more possibility. If you put the letters AQ after the formula, in parentheses, it means that it has been dissolved in water. And AQ actually stands for aqueous. From aqua, agua, that root. Aqueous solution. Now, but, yeah, Charlie. What? Jello is actually is a solid matrix with liquid trapped inside the little pieces. So it's actually a solid hanging on to a liquid, which is backwards from what we're used to. We're used to, we throw salt in and the liquid hangs onto the solid. It actually works the other way. You can dissolve some liquids in solids. Okay, so Jello, because it's got that protein matrix holding on to some water. Okay, now, everybody know the difference between liquid and aqueous? They sound a lot alike, don't they? What is the difference between liquid and dissolved in water? Okay, so the example that comes to mind for me is the Wicked Witch of the West. What were the Wicked Witches of the West's dying words? Remember from Miserable Oz what her dying words were? I'm melting! She said, I'm melting. WW solid goes to WW liquid. That's melting, right? So that's I'm melting in chemistry. Wicked Witch solid becomes Wicked Witch liquid. Okay? But she wasn't a scientist. She was wrong. Because how do you melt something? You heat it up, right? That's how you melt something. You heat it up. In Wizard of Oz, they heat up the witch. You don't remember how she died? She died because they threw a bucket of water on her. She ended up in the puddle. Threw the bucket of water on, she started steaming, said, I'm dying, and then you see her hat sitting on top of the puddle of water. Okay? Okay? Sugar, so what happened to her, what happens to sugar when it gets wet? It dissolves, right? So that is WW solid goes to WW aqueous. You should have said, I'm dissolving. Because that's what she was doing. Okay? So melting sugar is putting on the stove, put a pan on the stove, pour sugar in, turn it on, the sugar will melt, then it'll start to burn and it'll stink really bad. Okay? Dissolving sugar is take some water, add the sugar, stir. Difference between melting and dissolving. Difference between liquid and aqueous. Okay? Okay. There's a couple of specialties. You can use an upward pointing arrow after a product to indicate that it's a gas. Because a lot of our chemical reactions happen dissolved in water. And if you make a gas out of stuff that's dissolved in water, what's it going to look like? Make a gas with something dissolved in water. What are you going to see? You're going to see bubbles. Right? You see bubbles. And what's going to happen to those bubbles? What's in the water, they're going to rise to the top. So this arrow is saying, I'm making bubbles that are rising to the top. You can't use it for a reactant, you can only use it for a product. Because it's trying to describe what you see. I see bubbles going up. A downward arrow means that the product is a solid. And it's the same thing. You had an aqueous solution and you made a solid, that solid would sink to the bottom. So our adjectives are what state of matter they're in, solid, liquid, gas, or dissolved in water. That's our adjectives. That's how we modify the nouns. Okay? Now, we need the adverbs. We need to modify our verb. And our verb is the arrow. So we're going to modify the arrow. Okay. First modification is really bizarre. They take the arrow and cut it in half the long way and spin the bottom half around. You see that's what they did? Take the arrow, cut it in half the long way, turn the bottom half around. And that means that reaction is reversible. That means that reaction can go either direction. I'll have more on this later. Right now, we just need to know it's a possibility. It's the kind of reaction that happens in rechargeable batteries. Okay? Whatever chemical reactions happen in that battery, one direction it absorbs energy, the other direction it releases energy. That reaction can go either direction in that battery. So we know the chemical reaction in that battery has to be different than the chemical reaction in an alkaline battery. Because the alkaline battery, if you put it back, if you put it into a charger, just a regular alkaline battery, it will blow up on you. It will not turn back into a good battery. It will blow up. So there's got to be different chemistry happening inside those batteries. The one inside the rechargeable is reversible and more expensive. And the alkaline battery is cheaper, but it's one-time use. Right? So whatever that battery thing is, it's reversible. Okay? You can either put a triangle on top of the arrow. Actually, it's the Greek letter delta, it's not a triangle. Or you can put the word heat on top of the arrow to show that this reaction happens when you heat it. And if you stop heating it, it's going to stop happening. Ground beef, when heated, goes to hamburger. If I stop heating, it stops cooking, right? So we're not talking about where you have to put a spark to light the gas. The gas burn is the one that gives heat. The spark is not the heat. Okay? So as soon as you stop supplying the heat, that reaction stops happening. Now, I put heat on top. It could be any form of energy. It could be electricity. It could be light. Photosynthesis. Its chemical reaction is powered by light, so you put light on top of the arrow. Or instead of light, sometimes they write this. H nu. H nu, the Greek letter nu, E equals H nu, that is energy equals Planck's constant times frequency. Did that earlier this year. So by writing H nu on top, they're saying energy, light energy. If they write a chemical on top of the arrow, that means it's not on either side of the arrow. It's right in the middle. So it's not a reactant, it doesn't get used up. It's not a product, it doesn't get made. It's a catalyst. In this case, it's platinum. So whatever name of a chemical they put up there is a catalyst. That only leaves with one minor question we might want to answer after we know that you put the chemical on top of the catalyst. And that is, what's a catalyst? Okay. A catalyst is what's in your catalytic converter on your car. You studied catalysts before, but you probably didn't call them catalysts. A substance that speeds up a reaction without being changed by the reaction. I'll be very specific about what it does in just a few minutes. Okay. So it's an anti-pollution device. We'll talk about exactly which pollution it's getting out. Yeah. 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 So it changes the exhaust before it comes out the tailpipe. Okay. So it speeds up a reaction without being changed by that reaction. So if it's not changed, it's not a reactant, and it's not a product. You didn't make it, you didn't use it. That's why it goes on the top of the arrow. You studied catalysts last year, but you didn't call them catalysts. Remember what you called them? No, you did multiple labs with them too. Enzymes. Enzymes are catalysts that your body codes for in proteins. Enzymes are protein catalysts. The examples of catalysts of enzymes. Anybody ever eaten a lot of fresh pineapple?
What?
How did your mouth feel? Did not tingling and sore a little bit? Okay, here's why. Fresh pineapple has an enzyme in it. That enzyme breaks the peptide bonds in proteins. It tears proteins apart. Right? It speeds up the falling apart of proteins. So it's digesting your mouth. That's what's happening. It's the same enzyme in meat tenderizer. You buy meat tenderizer, it's the powder you shake on. It's the enzyme in pineapple. It's also in kiwi. Okay? If you eat a lot of kiwi, the same thing's going to happen to you. You can't make Jell-O with fresh pineapple because Jell-O is a protein matrix. If you put fresh pineapple in there, it's got the enzyme, destroys all the proteins. Your Jell-O will never set. If you want to put Jell-O, if you want to put pineapple in your Jell-O, you have to use canned pineapple. Because canned pineapple got heated. Heating destroys the proteins, which is the enzymes. So those enzymes aren't there. So you can put canned pineapple in your Jell-O, but you can't put fresh. Because it's got an enzyme that speeds up how fast peptide bonds break. So it's actually digesting your mouth a little bit. Okay? And the catalytic converter is about nitrogen dioxide. Nitrogen dioxide, if you look out across this valley in the summertime and you see that brown haze, that brown haze is nitrogen dioxide. Okay? It's brown gas. Okay? And the way it forms is they bring air into the engine. Air is mostly nitrogen and oxygen. And when you heat it up, those nitrogen and oxygen are going to combine to make nitrogen oxide. Nitrogen oxide falls apart into nitrogen and oxygen automatically. But it takes days. So you're breathing the pollution for days. But in your car, the exhaust pipe comes out and goes out this roundish, this oval-shaped box, the catalytic converter. And inside that catalytic converter is a mixture of platinum and palladium. That's why they're expensive, because they got platinum and palladium in them. Those are rare metals. Okay? And that catalyzes this so it happens before it leaves the car. So instead of taking days to happen, it happens before it goes out of your tailpipe. So we don't get, so you may say you see the brown. When I moved here 25 years ago, I moved here in August, and in November, I looked south and said, hey, there's mountains over there. Because I hadn't seen them. Because the brown haze had been that thick from August to November. So pollution's gotten better because of this. It's why you have to use unleaded gas. Unleaded gas, because the lead coats over top of the platinum and palladium, so they're not touching the gas anymore. So every pump you go up to says unleaded on it. They made the switch when I was in high school. You had both leaded and unleaded. Okay? And the catalytic converter is why we had to go to unleaded. It's because we want the catalyst to survive. Because you don't want to replace the catalytic converter. They're expensive. And so, those are our pieces. Okay? All we're going to add to that is, instead of writing out the whole word, we can write just formulas. So we've been writing chemical formulas. Are the chemical formulas like the formulas you use in math? In your math class? Chemical formulas like those formulas at all? No. Okay? Because, okay, so an equation in chemistry is not like an equation in math class either. An equation in math class is a mathematical relationship. An equation in chemistry is just a way of shortening the sentence. It's just a way of presenting all the information, but writing it shorter. It's like shorthand. And that shorthand will lead to some mathematical relationships, but it's not math when we write it. It's just a sentence. So just like chemical formulas are not math formulas, chemical equations are not math equations. What will that let us do? That will let us take this sentence and shorten it up a little bit. If I put solid iron 3 sulfide and react it with gaseous hydrogen chloride, I will form iron 2 chloride and hydrogen sulfide gas. So I mix two things, I mix two other things. That's a lot to write. We can present exactly the same information, shorter. It says solid iron 3 sulfide. So iron 3 sulfide, that means Fe has a 3 plus charge, sulfide's 2 minus. So iron 3 sulfide is Fe2S3, do the crisscross. And we want to say it's solid. So by writing this, I have taken care of solid iron 3 sulfide. Reacts with. How can I write reacts with? My conjunction, right? I need another chemical. I need a conjunction. So I'm done with reacts with. Gaseous hydrogen chloride. Hydrogen, chloride, they didn't use any prefixes. So I got to use charges, 1 plus, 1 minus. That's hydrogen chloride. And I want to say it's gaseous. That's gone. To form. How could I write to form? I'm changing from before to after. It's time for the arrow. Solid iron 2 chloride. Iron 2 means 2 plus chloride, Cl with a 1 minus. Oh, it's a solid, not gas. Solid, or I could have put the down arrow here instead. And hydrogen sulfide gas. Hydrogen's 1 plus, sulfide's 2 minus. If it doesn't have prefixes, I got to use charges. No prefixes, use charges, right? I want to say it's a gas. So this and this are just two ways of saying exactly the same thing. Make sense? Okay. So that's a good place for us to stop. I want you to read about equations over the weekend. That. And next week we'll spend writing and dealing with the fact that, hey, it says there were 2 irons here. There's only 1 iron on the other side. What happened to it? I can't create or destroy atoms, but my sentence seems to say I just destroyed an iron atom. Doesn't it? We're going to have to deal with that. Okay. So just 11-1 tonight? Or this weekend? Have a good weekend? practice writing names and formulas. I'll put some more practice sites for names and formulas up on there. That's not going for you. So I will do that. Have a pleasant day.